SolidWorks Simulation, Lecture 16, Flow Simulation, Part 4, Heat Sink Problem. We have already solved this problem using solid heat transfer modules or procedures. And we enter the coefficient of convection as 10 watt meter square K as a stagnant air, coefficient of convection. But there is a problem with solid heat transfer procedure, that the coefficient of convection is constant. You enter manually. But in reality, once the columns of this heat sink get denser and denser, actually the coefficient of convection does not remain constant. So that is the problem with solid heat transfer procedure. So we need to do it using a flow simulation procedure. So first of all, we load the software, flow simulation, and then load the toolbar. We only load the main toolbar, open a case, and it will prompt for lead creation, but this is a external flow problem, so we don't have to create any lead. So we can go ahead and do the second step. So we have finished with the first step, which is drawing of a model and opening a case. And now for the second step, the name of the project will take the default. The unit system take the default, and will change the analysis type to external flow. And there is heat involved in this problem, and there's no radiation, no transient, there got to be a gravity, otherwise the air won't go upward. But the upward here is Z direction, so I need to copy this one onto Z direction. So my gravity is in Z direction, minus Z direction. The gravity is here for the airflow, because the hotter air go upward and cooler air go downward because of gravity. And the direction of flow as Z direction. So in this page, I check there's heat and there's gravity, and the flow will be in Z direction. Now the fluid will be air, and the solid will be aluminum alloy 6061, and the roughness of the surface will be perfectly smooth, and the ambient temperature will be 20 degrees C and 1 atmosphere pressure, and this is velocity of the air. I will remain stagnant air. That means you can define a velocity of the air in the room, but for this problem I will let the air be still air or stagnant air. There's no velocity in the air. The air is still stagnant. So it gives me an external flow area, and I'll define the Z direction to be positive Z direction to be 5 meters, so that the hot air can go upward. So I define that the air upward would be 5 meters here. Okay. Now in the second step, we have defined that there's a heat involved in this problem and a gravity in Z direction, and also the flow will be in Z direction. The fluid is air, the solid is aluminum alloy 6061, and that's what we defined. And here in computational domain, we define the Z direction, the volume will be 5 meters high. So now for the third step, actually in the external flow there will be no boundary condition, but here I would define the heat source. So I choose the bottom surface and insert a in flow simulation tool, flow simulation. I will insert a surface source, and this surface source I will define as 28 watts, which is the power of a CPU, general CPU. So I have defined that the heat source will be 28 watts, and there is no inlet or outlet surface definition because it is an external flow field. So I finished with the third step. And the fourth step, goal, I will define a global pressure goal, velocity, and fluid temperature, and also solid temperature, the average value for these 4 items: the pressure, velocity, and fluid temperature, and solid temperature. Okay, these are the global goals. And for example, if I will measure the numerical values on this surface, I need to define a goal for it. For example, on this surface, I'll define a pressure, velocity, and fluid temperature, solid temperature goal for it, so that the procedure will calculate the numerical values on this surface using iterations and until it converges. So now I have finished with the definition of the whole problem, which is opening a case and then define that there's heat and there's gravity and the flow direction will be z direction, the air as the fluid, and the solid will be aluminum alloy. And in the third step, I defined a heat source at the bottom as 28 watts. And for the goal, I let the procedure calculate pressure, velocity, and fluid temperature as well as solid temperature on global and also on the target area for me. So I can go ahead and calculate the procedure. And it will take quite a while to proceed with this calculation. So I will stop recording right now. As you can see from the solver window, that the hot air will go upward because of the gravity in z direction. So if you forget to define gravity, or you define gravity in the wrong axis, the air will go down or go sideways. So you know that the gravity direction is wrong. So now I know that my definition of gravity is correct, and the hot air go upward, and it is still iterating to about 40 iterations, and it is still not converges, because if it converges, these bars will be green. So all the 8 items are not converging, so the procedure is still running. So I stop recording right now. Okay, the solver has finished. So now you can insert a cut plot on XZ plane and showing temperature. So this is the temperature distribution, but you can hardly see temperature inside, so you have to make the heat sink transparent so you can see the inside of the temperature distribution. But now you will show it back because we will define the temperature distribution on the heat sink surface. And this is the temperature distribution. Now I'll hide the cut plot. and I'll measure the surface temperature using point parameters. I'll insert a point parameter and then choose this surface and choose the indicators on this surface. Use pick point, and I'll pick several points here and show the solid temperature. So you can see that the solid temperature here is 380.54. So it is about 127 degrees C, 127. So you can do for yourself that you make the columns denser or sparse, and you will see that the result will be close to the numerical value for experiments. But in solid thermal analysis, the result will be different from experimental value. So this is very important that you know that the convection heat transfer coefficient will change by changing the geometry. So for this kind of problem, heat sink problem, if the columns or plates are very dense, you need to perform simulations on fluid solution instead of solid heat transfer.